Okay. So the binomial expansion is a study of expanding two numbers, expanding two parts. Okay. A plus B to the power n. Now A plus B to the power n looks so simple to expand, and for sure it is so simple to expand if n is small. But as n increases, still simple, but time consuming. Okay, so if A plus B is to be expanded to the power 0, we easily get a 1. So what some guy did, he got A plus B to the power 0, expanded it and just got 1, came back and did A plus B to the power 1, and this just gave A plus B. So the guy developed some interest and said, okay, it looks like they can take a pattern here. Say, okay, what about A plus B to the power 2? It's giving us A squared plus 2AB plus B squared. It's getting interesting. Let's see. A plus B power 3. This is the same as A plus B power 2 multiplied by A plus B. Now A plus B power 2 is A squared plus 2AB plus B squared, and then you have A plus B outside. So it's okay. Let's see now. A squared times A, we get A3 plus A squared B plus 2A squared B plus 2A B squared plus AB squared plus B power 3. Then we add the right terms if there are any. We have A squared B plus 2A squared B, so we get 3A squared B. We also have 2AB squared plus plus AB squared. We'll get 3AB squared, and then have B power 3. Okay, so you could go as well to A plus B power 4. So now you've seen that so far, once we reach 4, there's so much work involved. We have to expand this whole A plus B power 3 by A plus B for us to have power 4 altogether. So then the guy came back and said, okay, this looks like it can make some sense if you take it in a triangle form. You just concentrate with the coefficients. You leave the variables. Since I've chosen to use A and B, someone else can use X and Y, P and Q, U and V, A and B. So many variables can be chosen in any pair, C and D. So you say, okay, whoever chooses whatever variable that they choose, we can meet at the coefficients. So now, how do you meet at the coefficients? So you pick for A plus B power 0, you just have 1. For A plus B power 1, we have the coefficient of A and of B. Separate them like that. Then for A plus B power 2, we have 1. Then the middle coefficient is 2, and then 1. So if you look at it very well, it looks like from the second one there coming to the third, to get the middle number there, we just added the 1 plus 1, which are on top there. So this means if we go back, say, okay, for power 3 now we have expanded it. So let's see if what we suspected could make sense in the fourth row. So you say 1 and then add these 2 to give us the middle number, add the 2 to give us a 3, and then you put a 1 here. Let's see if the coefficients we have now after adding are the ones we have here after doing the actual expansion. So you can see we had 1, 3, 3, 1. So that's how the guy now was able to develop the whole triangle. So instead of me coming down to expand here, I know the one that has power 4 will just be 1 here. You add, you get a 4. You add, you get a 6. You add, you get a 4, and then have a 1. If it were power 5, we add, we'll get a 5. We add, we'll get a 10. We add, we'll get a 10. You add, you get a 5, and then a 1. So the whole thing can keep going, and it looks like a triangle. It has ones on the sides, and then the base has got different numbers depending on the power where you are. And the guy named this whole structure after his name, and nowadays we call it the Pascal's triangle. Okay, then when you're able to, so the Pascal's triangle now is giving us the coefficients. Now what happens with power 4? We want to expand by putting our A and B. How do we put them? If we go back to 2, you observe that, if you go back to 2, you observe that we have A squared. The next thing is A1, B will appear, and then B will pick the power as A disappears. If you go to 3, we have A3, the next thing is A2, and then A1. As B is increasing the powers, A is losing the powers. This means that for the fourth line, for the fifth line, I mean, where we have power 4, we'll have A4 plus, we pick the coefficient from the Pascal's triangle, which is 4. A should be power 3. It has lost 1 power so that B can appear. Plus, we have 6. So A2, B2 plus 4. A will now have power 1 as B go to power 3, and then we'll have B to power 4. So in the first term, we'll have B power 0. The last term, we'll have A power 0. So what you're learning here is that in the Pascal's triangle, okay, in the expansion, of A plus B power n.
Sir,
Hello.
can you kindly reverse the screen? I just want to copy the last. Yes.
So in the expansion of A plus B power n, we've observed some things here to do with the powers that, so I'll keep going and getting back, that we note that the powers of A decreases as the powers of B increases, and the first term has only A to the power n, and the last term has only B to the power n. Okay? So after you notice that, then you can see that you can now easily use the Pascal's triangle if you are forced to do so. Sometimes some questions can be phrased, expand, for example, example 1, a question can come and say, expand x plus 2y power 4 using the Pascal's triangle. Okay, so ensure that you are all muted for the sake of the recording. Okay, so you say expand x plus 2y power 4 using the Pascal's triangle. So what do? If you have a triangle somewhere already, you just come here and say, okay, I want to get power 4. So our interest is just power 4 in this whole thing. Okay, so in power 4 we have 1, 4, 6, 4, 1 as our coefficients. So say, okay, here we should have x plus 2y power 4 having the coefficients. The first one we said it is just a to the power n. The second one has 4 in the Pascal's triangle, and then x power 3 as 2y appears to the power 1, plus in the Pascal's triangle we have 6. We have 6 x power 2, 2y power 2, plus 4 x power 1, 2y power 3, plus 2y power 4. Then you simplify, so we get x4 plus 8 x power 3y plus 2 squared is 4. 4 by 6, we get 24 x squared y squared plus 2 power 3 is 8. 8 by 4 is 32 x y power 3 plus 2 power 4, that is 16 y power 4. So that will be our expansion using the Pascal's triangle. So some questions can specify. Okay, but now look at this. You may really want to use the Pascal's triangle, and then you meet a question. Let's say example 2. It comes out and say, okay.
Excuse me, sir.
Okay.
I'm asking about the previous, on this example where you have found this 16. 16y is
Power
4
4.
square. Yes, powerful.
So 16 is 2 to the power 4.
Okay.
Yes. Okay. So I can't see the one who is not muted. Okay, there's a hand from Annie.
Yes, sir. Sir, I was just asking on the multiplication, how it's being done. Like when you get those numbers from the Pascal's triangle, how do you now apply them? Because I've seen you splitting the x's and the y's.
So when we are saying in this case, A is x, B is 2y. Okay. And then we have it here, is it? This is to the power 4. So all we're doing is we are substituting where there's A, we are putting x, where there's B, we are putting 2y. When we are done having them in this form, we come back and realize that the 2y to the power 2 means 2 to the power 2 multiplied by y power 2. But 2 to the power 2 is 4, so we multiply 4 by 6 to get 24 and then leave the variables alone. That's how we get to do our multiplication there. The thing is that if you have constants, if you're asked to multiply 3, to simplify 3x, y multiplied by 4z, you'll be so comfortable to leave it as 12 x, y, z. You realize that 4 can be multiplied by 3 to give you a 12, and then the variables remain alone. That's what we are trying to do when we are separating that constant 2 to any power, bring it down to the other variable. Okay. Do we have a question? Okay, so if we have no question, kindly mute. So if we have another example, let's say we have example 2 where we are saying expand the same x plus 2y, now we put to the power -1. And you want to see if you can expand this. When you get back to the Pascal's triangle, what you will find there is the power starting from 1. I mean from 0, 1, 2, 3, 4 going up. So then we are stuck. How do you do that expansion? Okay. So what you do now is, this is a point where Isaac Newton came in now, said, okay, why can't we start this Pascal's triangle in a broader perspective? So the guys got the Pascal's triangle, did some expansion in the increasing numbers, and then they realized that you could actually write, instead of having the Pascal's triangle, you can actually have the binomial theorem. Okay, which was now a generalized form of the Pascal's triangle. So I said, instead of troubling ourselves to always getting the Pascal's triangle, why can't we have this structure here? an-1 plus n2, so b will appear here, an-2 b squared plus n3 an-3 b3. Going, if you find a term you don't know, you can put a general error there and say an-r br, and keep going until you end at n to the power bn. The same thing we noticed when you're looking at the Pascal's triangle, where the first term had a power n and the last term had the b power n. The same thing is still happening here. Okay, except when you reach here now, you must understand what it means to have n0 and how we read it. So the guys came up with this definition in the form of n, and they accordingly choose r. So you could write it in this form or just write it in this form, where you define it as n factorial over r factorial and then n minus r factorial. The purpose of this nr is to give us the coefficients that we are obtaining using the Pascal's triangle. The Pascal's triangle has already given us a pattern of the powers of a and b. That the powers of a will decrease as the powers of b increases. What's on?
Sir.
Hello.
Hello, sir. Hello.
Hello.
Yeah, yes, sir. Do you apply the binomial theorem when the power is negative on fraction?
When the power is negative and a fraction. Yes.
Oh, okay.
So you see now what is going to happen here. So after they get the generalized form of this theorem, the n choose 0, n1, n2, n3, nr, nn, all these are just giving us the coefficients that we are obtaining using Pascal's triangle, except that Pascal's triangle did not talk about the negative n. But this theorem also cater the negative powers. It also deals with the fraction powers. But at which point do you get to deal with those? You must first understand how to calculate n choose 0, n choose 1, n choose 2, n choose 3, all the way up to n choose n, so that you're able to see how they relate directly to the Pascal's triangle. So after having this definition of n choose r, you are saying you can now obtain 1 n choose 0. So what will be n choose 0? N choose 0 is the same as n factorial over 0 factorial n minus 0 factorial. So to have this make sense, we must have a definition of 0 factorial and also a definition of n factorial. We've just seen them being written here. What do they mean? So the definition of these guys, starting with 0 factorial is just 1. 0 factorial becomes 1 to avoid making this whole work useless, because n factorial is defined as n multiplied by n minus 1 multiplied by n minus 2 multiplied by n minus 3. You keep multiplying by numbers, reducing by 1 without skipping any whole number until you get to n minus n factorial. But you understand that n minus n is just what? So you can keep going until you get to 0 factorial, because n minus n is 0. So if 0 factorial was defined as 0, this whole multiplication could be 0, and then you won't do anything. So now it was restricted to be 1 so that it can make sense. So now when we get back to this, we are saying this is just n factorial over 0 factorial is 1 multiplied by n minus 0 is n factorial. But in mathematics, if you are dividing n number over itself, even if you don't know what that number is, it's okay to say what you get is 1. Okay? N factorial divided by itself, automatically we get 1. Okay? This means that as the Pascal's triangle guides, the first number will always be 1, the first coefficient. As we can see in this triangle, that the first coefficients are 1s. Calculating using the theorem, we've also obtained a 1. 2, you get n choose 1. By definition, this is n factorial over 1 factorial multiplied by n minus 1 factorial. Now 1 factorial is just 1 because it will be 1 multiplied by 0. factorial. And 0 factorial is 1. So you get 1 by 1, which is 1. So I can put it here. 1 factorial is just 1 multiplied by 0 factorial, which is 1 multiplied by 1, which is 1. 2 factorial, this is 2 multiplied by 1 factorial, meaning it is 2 multiplied by 1, which is 2. So I'm trying to explain what we mean by n factorial and the multiplication going down. So if you have n factorial over 1 factorial multiplied by n minus 1 factorial, it's the same as having n factorial over n minus 1 factorial. Okay. Now, since we have defined the n factorial as a product going down, the guidance is that you may wish to stop anywhere, and you are free to do so, provided that when you stop, you put the factorial. So in this case, we'll have n multiplied by n minus 1 factorial, and then to avoid repetitions, once you notice that the number you have on top is also down, you stop there, because you know that in mathematics, dividing the same number by itself gives you a 1. So we'll have n multiplied by 1, which is just n. And for sure, we have seen on the Pascal's triangle that when n is 4, the first coefficient will be 1 and the second will be 4. When n is 5, the first coefficient will be 1, the second will be 5, meaning that the first coefficient is 1, the second is n. When n was 3, the first coefficient was 1, the second was 3. So the theorem is bringing back all the coefficients of the Pascal's triangle. Then next, let's see what n choose 2 is. This is going to be n factorial over 2 factorial multiplied by n minus 2 factorial. This is the same as n multiplied by n minus 1 multiplied by n minus 2. But look, if you put a factorial here, this number n minus 2 can be found in the denominator, n minus 2 factorial. So what will this mean? You can cancel there, you can cancel here. So you get n multiplied by n minus 1 over 2 factorial. Okay, we leave it there. Let's go to n choose 3. N choose 3 will give us n factorial over 3 factorial multiplied by n minus 3 factorial. This is the same as n minus 1, n minus 2, n minus 3. If we put factorial, we'll have this number down. 3 factorial by n minus 3 factorial. So this n minus 3 factorial and this one can take each other, so that we just have n minus 1, n minus 2 over 3 factorial. So in application questions, this is how far we go in knowing the coefficients. But you understand that if we went as far as n choose 4, we could still find the value, because we are saying this is n factorial over 4 factorial n minus 4 factorial. So you get the numerator, reduce it, reduce it, reduce the multiplication, keep multiplying. But once you mention n minus 4, you know it is there in the denominator. So you can end there on top, because this part will cancel that part. And so you remain with n minus 1, n minus 2, n minus 3 divided by 4 factorial. Okay, so let's see if let's see what happens. So let's see what happens if we multiply, if we bring in small numbers. Let's see, we want to do a plus b to the power 4 using the formula, using the theorem. So it will be 4 choose 0 a power n. It will be 4 choose 1 a power 4 minus 1 b power 1 plus 4 choose 2 a power 4 minus 2 b power 2. It will be 4 choose 3 a 4 minus 3 b power 3. It will be 4 choose 4 a to the power 0 b power 4. Okay, then what have we said? We've said that n choose 0 is just 1, so 4 choose 0 is just 1. So we have so here we're supposed to put the actual n, which is 4. So here we'll have a power 4. Naomi?
Sorry, sir, it's a mistake.
Okay. So we have a to the power 4 there. Since we said 4 choose 0, according to n choose 0, we said n choose 0 is 1. So no need of calculating. N choose 1 is n. So when you have 4 choose 1, we get 4. A to the power 3 b plus 4 choose 2. We are here now. 4 choose 2 is just 4 multiplied by 4 minus 1, which is 3, and then divide by 2 factorial, which is 2, and then a squared b squared plus 4 choose 3 is here. We said it's just 4 minus 1, which is 3, 4 minus 1, which is 3, 4 minus 2, which is 2, over 3 factorial, which is a 3 by 2, and then a to the power 1 b power 3. 4 choose 4 is 4 minus 1, which is 3, 4 minus 2, which is 2, 4 minus 3, which is 1, over 4 factorial, which is 4 by 3 by 2 by 1 b to the power 4. So we're noticing that this is a power 4 plus 4a3b plus 2 here, 1, 2 there, 2. So 2 by 3, we get 6. A squared, b squared, plus 3 here, 1, 2 there, 1, 2 there, 1, 3 there, 1. So we get 4a b power 3 plus 4, 3, 2, 1. 4, 3, 2, 1. So we just get b to the power 4. Okay? And for sure, this is the expansion that Pascal's triangle gave us. So remember, we had the expansion here. A power 4 plus 4 a3b. Daniel?
Yes, sir. Sorry, I'm a bit confused. Where are you getting those 3? Yeah, 3. Then there's 3 there. Then there's a 2 there.
So what we are doing is we are getting them from what we have calculated here. We said n choose 2 is n multiplied by n minus 1 over 2 factorial, where 2 factorial is just 2 times 1. So if you have 3 factorial in your denominator, then you're having 3 by 2 by 1, according to the definition of n factorial. So if you have 4 factorial, then you have 4 by 3 by 2 by 1. That's what factorial means. So whenever we are seeing a factorial in our denominator, from the general calculated ones, we are substituting our n. In this case, n is always the power, so our n is 4. So whenever there is n in the formula, we are taking 4 all the way until we get to 4 itself down here. Is that okay?
Yes, sir. Thank you.
Okay. So you've seen that the formula is actually giving us what Pascal's triangle gave us. Except that this formula now can be written, instead of us having it in this general way of n choose 0, n choose 1, we can as well choose to write it as a plus b power n. Now that we know what n choose 0 is, n choose 0 is just 1, so we can just write it as 1 multiplied by a power n plus, you've seen that n choose 1 is just n, so where there is n choose 1, we'll just put n. So we'll have n, it is being multiplied by a n minus 1 b plus n choose 2 is just n minus 1 over 2 factorial, so it's just n minus 1 over 2 factorial a n minus 2 b2. n choose 3 is just n minus 1 n minus 2 factorial over 3 factorial a n minus 3 b3. So you can keep going in this manner. Since we have calculated the first few terms, so you can see that instead of having n choose 2, n choose 3, I can write them in the simplest form calculated here. Okay, what does this help us? This will help us now. For example, let's go back to example 3. Let's go back to example, was that example 3 or example 2? Okay, it was example 2. So let's go back to example 2. So example 2 was x plus 2y power negative 1. So expand x plus 2y power negative 1 up to and including the term in x power 3. So it means that we must expand all the way up to x to the power 3. Okay, so now let me change, instead of saying x power 3, let me say y power 3. Y power 3. Up to include the term in y power 3. Okay, so you can start. Solution. You have the form already. Just identify what a is. So a is x, b is 2y, n is negative 1. So we have x plus 2y to the power negative 1, giving us a is x to the power n, which is negative 1, plus b, we go to n is negative 1, a is x to the power negative 1 minus 1, multiplied by b, which is 2y, plus n is negative 1, then negative 1 minus 1 over 2 factorial is just 2, and then A is x, -1 minus 2, B is 2y to the power 2, plus -1, which is n, -1 minus 1, -1 minus 2. So in fact, there's no factorial there, over 3 factorial, which is 3 by 2. And then x power -1 minus 3, 2y power 3. So you could keep going, but the question says you must end in the term y power 3. So we have found y power 3, so we can end there. This can be simplified as x power -1 minus x power -2 multiplied by 2y, and then plus, this is -1 multiplied by -2 over 2 x power -3, 2 power 2 is 4 y squared, plus -1, -2, -3 over 3 by 2, 2 power 3 is 8, and then x power -4, y power 3. So if you keep going, we can simplify now. We have x power -1 minus 2x power -2y, and -1 multiplied by -2, we get 2. 2 over 2 is 1. So we have plus 4 x -3 y squared, and then -1 multiplied by -2 multiplied by -3, we get -6. -6 over 6, which is 3 by 2, we just get -1. So we have -8x power -4 y to the power 3. So you've seen that even to the negative power, the binomial expansion can still give us the expansion that is required. So now this was a generalization by Isaac Newton, when he saw that Pascals ended only on the positive coefficients, positive powers. But this one can also give us fractions. So now look at how nice it becomes if Naomi.
Yes, sir, I didn't get it in the first equation.
Which equation? Which first equation of the question, or the one on top?
No, this very one was just from solving. In the first equation, how you found x to the power 1 plus -1. Just there.
Of x to the power -1
Yes.
going down. So we are having this. We are having this general expansion there. So we have first identified what our a is in the question. If we compare the two, a will be x, b will be 2y, and n will be -1. Then you go back in the same and substitute in that order. So we have x plus 2y to the power -1, which is n, is equal to, instead of having a power n, a is x, n is -1. So we'll have x to the power -1.
All right.
Plus, okay, good. Now look at how nice it becomes if the same one, you specify your a. If your a was to be 1, and on the b part, let's put ax and fix the n. Okay? So in the same theorem, the same expansion, we now specify that the first term is 1 plus ax to the power n. Okay, this means that a is 1 and b is ax. We want to use this now here to fit it in the star equation there. So where there is a, we have 1. 1 power n is still 1. Plus n, where there is a, we have 1. 1 power n minus 1 is still 1. So you just write b. Plus n minus 1 over 2. 2 factorial is just 2. When there is a, we're supposed to write 1 power n minus 2. But 1 is just 1. To n power is still 1. Multiplied by b, but b is ax squared. Plus n minus 1, n minus 2 over 3 factorial, which is just 3 by 2. Where there is a is 1. 1 power n minus 3 is still 1. So just write b, which is ax power 3. So you can keep going. So you can see that the one which has a 1 as our a becomes very easy to use. It's so nice because you only pay attention to the b part because the a is not changing anything. So let's do example. Let's do an example so that you can see how to use this one here. Example 3. So expand expand 1 plus 2x to the power half up to and including the term in x3. So when I'm ending at x3, this is where most questions, most application questions will end at 3, even if you are not told. The only expansions we go beyond power 3 are those expansions that will require you to use either Pascal's triangle or maybe they specify a positive power. Expand a plus b to the power 5. That's when you go all the way up to you finish all the terms, because when the power is 5, the terms will be 6. So you bring all of them. But if the power is negative or a fraction, you go as far as x power 3 in most questions in this course. So we have a general one, which we just saw that it's 1 plus n ax plus n minus 1 over 2 ax squared plus n minus 1 n minus 2 over 3 factorial, which is 3 by 2 ax ax power 3. We had end at power 3, so we come down now and get our question 1 plus 2x to the power half. So our n is half, so we're just substituting half, and our a is 2x. I mean, our ax is 2x. Is that a question?
Yes, sir.
Okay.
will it be?
If you put,
5 or negative 10 on 1.
okay, don't worry. We have an example of that nature. Okay, so we have 1 plus half multiplied by 2x plus half as our n, half minus 1 as our n over 2, then 2x power 3, 2x power 2 plus half our n, half minus 1, half minus 2 over 3 by 2, 2x power 3. Once you reach power 3, the question says up to and including the term in x3. So we leave it there, come down to simplify. So I have 1 plus x, because half times 2 is just 1, plus we have half. Half minus 1 is negative half. And then 2 power 4, 2 power 2, that is 4x squared. So I'll put the over 2 here, plus half. Half minus 1 is negative half. Half minus 2 is negative 3 over 2. And then 2 power 3 is 8. X power 3. And then I'll put the 6 here. You can keep going. So you come down and say, this is just 1 plus x minus, so 2 by 2 can give us 4, so to take away the 4 on top there, so we just have x squared over 2, and then here we'll have plus, because negative times negative is positive, so we'll have plus 2 times 2 times 2 will give us 8, so to take away the 8 that is there, and then the 3 here will reduce 6 to 2. So we get x3 over 2. You keep going like that. So you'd leave your expansion here. So you can see that when our a is 1, this expansion is nice to use and you easily get to the answer. They'll also ask you, say, hence, find the range of values of x for which the expansion 1 plus 2x to the power half is valid. Your solution, just get this part here, put it in the modulus, make it b less than the a part, provided that your a part is positive. Okay, now you understand that every number comes out of the modulus as a positive number, and then divide, so you'd get the modulus of x to be less than half. We did inequalities, and we saw that this is just the same as negative half, less than x, less than positive half. Okay?
Oh, sir, repeat on the same question.
So when you're asked to find the range of values of x for which the expansion is valid, your target is to get the b part. When I say the b part, I mean from a plus b to the power n. Ensuring that your a is positive. Get the b part, take it in the modulus, let it be less than the a part. So I'm sure now you're asking, what happens if the A part is negative? That is our next example now. So that can also answer the question for Watson, where what if, while there is 1, we have a different number? That will be our example 4. Hello. Is that a question?
No, I want to get a
Yes,
screenshot.
so when
Okay. The one asking?
finding the range there, what if you solve for x in the brackets, then you know that the range is from negative to a positive, the number you find. How is that?
You get 1 plus 2x and equate it to 0.
Yes.
And so for x, it will give us what? Suppose we had 1 plus 2x is equal to 0. We'll get x is equal to negative 1 over 2. And then
You conclude that the range is negative 1 to positive, or negative 1 over 2 to positive 1 over 2.
it's still okay.
Okay.
As long as you're able to conclude in that way.
Okay.
But as you conclude, you're using this definition, is it?
Yes.
All right. So why not just using the definition?
So how did you find the negative 1 over 2?
So you have forgotten one concept of inequalities. Remember what we are doing when you find an inequality question, they ask you to solve for x plus 1 less than positive 4. What are we doing? We said this would be negative 4 less than x plus 1 less than positive 4. Is it?
Yes, sir.
So from this definition, when you have this less than half, you can as well say it is negative half less than x less than positive half. But if that day you're only able to get as far as here, please don't bother yourself to start remembering what we did next. Just leave it. This answer is correct. It gets same marks as this one here. So don't stress. That how do I remember that? What if I forget? If you forget one, or if you don't like inequalities, just leave it on the modulus less than half. It's still okay. Example 4. Expand negative 2 plus 3x to the power negative 1 up to and including the term up to and including the term in x3. So the term is refusing to be written here. The term in x3. Okay? Solution. You know that it's easier working with a 1 there. So your target is to get rid of this negative 2 in that position. So you say, okay, if I go inside the brackets, I factor out a negative 2, I'll have 1 here plus 3 over negative 2x close. This is all to the power negative 1. So if we give the power to negative 2, we'll have negative 2 to the power negative 1, and then we'll also remain with 1 minus 3 over 2x to the power negative 1. But you understand that negative 2 to the power negative 1 is just the same as what? It's just the same as negative 1 over 2 to the power 1. That's why I've said negative 1 over 2. And then you have 1 minus 3 over 2x to the power negative 1. So we have made the A part positive, so that when they ask us to find the range of validity, you will just get the modulus of negative 3 over 2x less than 1, our A part. What about the expansion? We'll keep the negative half outside because it is to the power 1, so there's nothing to do there. Then you expand what is inside. So it will be 1 plus the power is negative 1, where you're writing n, multiplied by negative 3 over 2x plus n minus 1, that is negative 1 minus 1 over 2, negative 3 over 2, negative 3 over 2x, negative 3 over 2x power what? X power 2 plus negative 1. So because of space, I'll calculate negative 1 minus 1 is negative 2, and negative 1 minus 3, minus 2 is negative 3. Everything over 3 factorial, which is 3 by 2, and then negative 3 over 2x
Sir,
to the power 3. Hello.
excuse, I'm sorry, my network kind of tripped. Why are you multiplying by 1?
Why
Then
multiplying by 1?
1 plus 3 over negative 2x.
1 plus 3. Why multiplying by negative 1 here?
No, like, how did it change to that? From the question, how did it become like that?
Okay. So from the question, what we had is negative 2 plus 3x to the power negative 1. But we've established a very nice expansion here that if you have a 1 in the first position, it becomes easy for you to expand because you only pay attention to the B part. So we're trying to use the advantage from here to say, why can't we force a 1 in the first position there? So to force a 1, if what we have here is a constant, it's easy to force a 1 because you just factor it out, give it a power, then you remain with the expansion that has a 1 as your first element in the brackets. So I have to factor out negative 2. When you factor out negative 2, it affects every part of the inside. So it divides 3. So that you have negative 2, you give it the power negative 1, and then you have 1 minus 3 over 2x to the power negative 1. But once you have that expansion there with a 1 as your first term, then you easily bring down the expansion that is coming from this one here. That's how nice it becomes now. Derek?
Yes, sir. Where do you get negative 1 over 2?
Negative 1 over 2. If you have x to the power negative 1, it's the same as 1 over x, is it?
Yes, sir.
So if we have negative 2 to the power negative 1, it must be the same as 1 over negative 2, is it? But this is the same as
Yes.
negative 1 over 2. That's where we get it from.
Thank you.
Okay. So whenever the power is negative, you are able to make that power positive by taking that whole thing in the denominator. Okay, so now we have the negative half outside still, then we go and simplify inside. So we have 1, negative 1 by negative 3 over 2, we'll have positive 3 over 2x, and then plus, we have negative 1 by negative 2, because this is the same as negative 2 here. So negative 1 by negative 2, you get 2. 2 over 2, you get 1. So negative 3 squared, that is 9 over 2 squared, 4x squared. And then we have again negative 1 by negative 2 by negative 3, that is negative 6 over 3 by 2, which is 6, that is negative 1. But the negative inside the brackets is to the power 3. So power 3 negative, the negative will come out, and we have negative 1 remaining after dividing 6. So now we'll have that negative by the negative remaining outside. We'll have a positive, and then 3 to the power 3 is 27. 3, and then 2 to the power 3 is 8. X power 3. So there's a question. Oh, it has gone. Okay. So the constant outside, you just leave it there. Because in mathematics, if there's anything common, we factor it out. So if it is already out, there's no need of multiplying it. We love it when it is outside like that. So this is the expansion up to power 3. And then let's add, find the range of values for which the expansion is valid. So you say, okay, we'll pick it from here. Get negative 3 over 2x, make it b less than 1. Forget about the half which is outside. We are just talking about what is in the brackets, because that's where the expansion is. That number outside, it is still outside. It is still outside until we are done with the expansion. So any number that comes out of the modulus comes out as a positive number. So 3 over 2, and the negative won't remain inside. No negative survives in the modulus. Less than 1. And then how do you get rid of this? You just multiply by 2 over 3. Multiply by 2 over 3. Multiplying by 2 over 3 is the same as dividing by 3 over 2. So don't get confused there. So you have the modulus of x less than 2 over 3. Like that. This is the range of values of x for which the expansion is valid. Is that okay? Have you seen why I was saying that binomial is in 2 sessions? It's even too much for 2 sessions.
True, sir.
Because only a few parts here are remaining. Finding a general term and some application questions where they give you the terms. Then you have the expansion. Then you compare to get some missing variables, some unknown variables. Then also you're asked, because these are series that we have done now. Given that expand after including the term in X3.
The proof in
Nani
part
Shehu?
C.
Yes, I have a question there.
Okay.
On how did you get the 2/3 part? That part.
The 2/3 part. Okay. So what we had is 3/2 less than 1. And then we divided by 3/2. We divided by 3/2. So we meant with the modulus of x is less than 1/3/2. But look, this is the same as 1 divided by 3/2, which you can write as 1 multiplied by 2/3, which is just going to be 2/3. That's how it became that.
All right, sir.
Okay.
So,
Hello.
so just to like avoid complications of maybe forgetting that you factored out that -2, isn't there like a way to just work with it from the beginning?
No, the way is there. And what is the way? What is the way? This is the way. And as you do it, you will feel the pain of not factorizing it. Because -2 will keep coming and with different powers, and you have to evaluate it at that power. And then evaluate the other part with its powers, and then combine the powers. So you should love factorization. Okay. Then,
Sir, sorry. Yes, sir. So
hello.
this last equation is only applicable when you are dealing with fractions and negative, if n is negative or a fraction.
In most
Oh,
cases,
okay, sir.
yes. Okay, another example. Before we start overthinking. Example 5. Okay, since we saw that in this expansion, in the original expansion, in the binomial theorem, you've seen this term here. This term here. This term is called the general term. And how you come about, how it comes about, you are observing what is happening at each term. The first term, the down number here is 0, and yet you are calling it the first term. The down number here is 1, and yet you are calling it the second term. The down number here is 2, and yet you are calling it the third term. The down number here is 3, and yet you are calling it the fourth term. This means that the term is ahead by 1 to the number down. So if you want to write this number here, if you want to write that term, we'll say it is term r plus 1. Okay? And we also saw that this power, this 2 is what we subtract from n and is what we give b. That's the more reason why we subtract the r from n and it becomes the power of b. So how does this help us? This will help us to answer questions that comes in the nature find the eighth term in the expansion of x squared plus 2 over x to the power 11. The solution, you always start with t r plus 1. The general term is n r. When you put a, you say n minus r. B, you give it power r. Then go back to your question and identify what a is, what n is. Now you understand that n is always the power. So n is the power. Now look, we've been taught the position of the term, the eighth term. So we want to write T8. What does it mean to us? It means that r plus 1 is equal to 8. So r is 8 minus 1, which is equal to 7. So when you say T8, n is the power, r has been found, a is x squared to the power n minus r, b is 2 over x to the power r. Then you simplify. So first thing to simplify is 11 to 7. What is 11 to 7? We say this is just 11 factorial over 7 factorial, 11 minus 7 factorial, which is 11 factorial over 7 factorial multiplied by 11 minus 7, 4 factorial. Then we start 11 by 10 by 9 by 8 by 7. Once you mention 7, you stop there because you know that there's a 7 down. In mathematics, these numbers are equal. So when you divide, you get 1. Then just reduce your 4 factorial to 4 by 3 by 2 by 1. Then this 7 factorial and that 7 factorial will go. So we remain now with 4 by 2 is 8. So that 8 there can go. 3 in 9 goes 3 times. So now we have 11 by 10, that is 110. 110 by 3, that is 330. So you have 330 there. So you go back and say 330 multiplied by 11 minus 7, that is 4. And you know that if you have a power n to the power m outside, this is the same as a power m multiplied by n, or a power n multiplied by m. You can switch them in any way because that's multiplication there. So we'll have 330, 11 minus 7, that is 4. So we have x, 2 by 4, that will be 8. And then 2 power 7 over x power 7. You guys must understand that when you're having a over b to the power n, this is the same as an over bn. Okay, so this is the same as 330 multiplied by 2 to the power 7, and then x power 8 over x power 7, that is just x. This would be our term. We've used the general term understanding to get the value of r, and then we've used the r to have this term here. Now on the term, you must not relax here. You should also expect questions of this nature. Example 6. So example 6, you should expect the term mentioned in this way. Find the term independent of x in the expansion of,
Sir,
hello,
sorry, want to see the previous board.
okay, it's here.
All right, thank you.
Okay. So find the term independent of x in the expansion of that. Now we have not been told the term position. This means that we may have difficulties in knowing what our R is. So we'll leave it like that. First thing to write, whenever they talk about the term, you first write this thing before you start being confused. N is always the power. So you have 12 there. You don't know what R is. A is x. 12 minus R. B is negative 1 over x to the power R. Is still okay? What we do next? Say, okay, this 12 is R. They are saying the term independent of x. That language there is asking for the term, for the constant term, the term that will not have x. That's what we mean in independent of x, meaning that term is without x. So put the powers of x together. So put the x's together. So we have x, 12 minus r. That negative there can be considered as negative 1. Give it power r. And that x there, because it is down, let it go up and just make sure the r becomes negative. Okay, since we say that whenever you have x to the power negative 1, it's the same as 1 over x. Even in reverse, it is still correct. An equal sign means that the reverse and the forward way are the same. Okay, so from there, you get, we're now saying this is 12 r negative 1 power r, and then x. Because we have the same base, we can add the powers. So we have 12 minus 2r. Now the term independent of x will be the term whose power of x is 0. Because you guys understand that x power 0 is what? Is 1. That term doesn't have x. So we will require that x 12 minus 2r be equal to x power 0. Because the bases are the same, this demands that 12 minus 2r be equal to 0. So this is the same as negative 2r is equal to negative 12. Divide by negative 2, divide by negative 2, r is equal to 6. So when r is 6, you come here and say 12 in this one. 12 choose 6 to the power negative 1, negative 1 power 6. And then there's no need of saying x 12 minus 2r because you are sure it will be 0 there. David? It was a
Oh,
mistake.
sir. And yes, sir. No, it wasn't a mistake. I'm a little
Okay.
bit behind. I'm a little bit behind on how you got R. My network cut. Sorry.
So for you to get R, you get back to the question which says the term independent of x. The term independent of x is the term without x. And the term without x, when the x is appearing there, is a term whose power of x is 0. Because x power 0 is 1, and 1 doesn't have any x. So what we'll do is, after we put the powers of x together, we only have x appearing once with that power there. You make sure that that x appearing must be equal to x to the power 0. Okay? This is only possible when the powers are equal. So you say 12 minus 2r is equal to 0. Then look for r now. So r will come out to be 6. From there, substitute. So when you substitute, if you insist to substitute where there is x there, you say 2 by 6. You understand that this is just 12 minus 12. 12 minus 12 is 0. X power 0 is 1. So we have no x anymore. So we just have 12 to 6. Negative 1 power 6 is positive 1. So we forget about it. Then find this now. This is 12 factorial over 6 factorial. 12 minus 6 is again 6 factorial. Don't forget the definition of factorial. This is 12 by 11 by 10 by 9 by 8 by 7 by 6. Once you mention 6, you stop there. Because you know that there's a 6 down. So you expand 1, 6, 6, 5, 4, 3, 2 by 6 factorial. So since we have 2 6s here, we've expanded 1 and left the other so we can take away that one. Then now you start 6 by 2 is 12. So they can take away the 12 on top there. Then you have 5 in 10, that's a 2. You have 4 in 8, that's a 2. We have 3 in 9, that's a 3. So that is 2 by 3, 6 by 2, 12. Then 11 by 7, 77. So now we are dealing with 77 multiplied by 12. Okay, this should be an easy thing to do. 2 by, so let's multiply it like, suppose you have no calculator. So you do 2 by 7, 14, carry 1, 14, 15, 0, 7, 7. So you get 4, you get 12, carry 1, you get 8, 9. So this is 924. But if the gap is too big, or if the numbers are too big, you can as well leave it here. If you had to lose marks, you may only lose maybe 1, but you're trying to save time to do other things. So this is the term independent of x. So this does not mean that they cannot ask you, they cannot specify the power of x they want you to find. They can specify. They can specify. In this same question, they can say, suppose we say, they can still say, find the term. They can still say, find the term in X4 in the expansion of the same, that is x minus 1 over x power 12. So you do the same thing. You start it the same way until you get here. When you get here, instead of equating this to x power 0, you equate x 12 minus 2r to x power 4, because they want it in x power 4. And then you know this is only possible when 12 minus 2r is equal to 4. So that is negative 2r is equal to 4 minus 12, which is negative 2r is equal to negative 8. Divide by neg 2, divide by neg 2. So we are getting r is equal to 4. There you go back and say t 4 plus 1 is equal to, you substitute 12, r is 4 now. Remember there was a negative 1, power 4. Then now you write x, 12 minus 2, 4. This will give us 12, 4. And then negative 1 power 4, that is just 1. So you get x, 12 minus 8, that is 4. You can evaluate 12 to 4 if you have time. If you have no time, you can just leave it like that. But when numbers are small, you better calculate. Don't be lazy. So you can start the same question. If they say independent of x, they mean you put together the powers of x and equate to 0. If they say the term in x power 4, you put together the powers of x and equate them to 4. Finding the term independent of x is the same as being asked to find the constant term. Sometimes they can say find the constant term in the expansion of x minus 1 over x to the power 12. The constant term is the term without x. You've seen it's a constant term. Sometimes they can be funny. They can ask you to state the position of the constant. So after you find r, then you go back to the left and say t6 plus 1. So this is the 7th term. If they ask for the position, you know where you take your r. You take your r here. Since we established that that term will be t r plus 1. Okay. So in the next session, if you don't miss, we're going to finish binomial, because we'll just look at some identities there and then some series applications. Then some few questions where they give us some terms to calculate some coefficients. So because we can't finish binomial in one session, it will be as if you are watching a movie, then you forget. So we'll leave it here.
Yes,
Okay.
I think you can leave it here because we are loaded.
Thank you, sir. Have a good
Sir.
night.
Hello.
So we don't factorize this one after finding the term form.
What do you mean factorize?
We don't put the 12 factorial, 11 factorial, we bring it down. When we find the x to the power 4.
No, you can. You can actually calculate this. 12 choose 4 is the same as 12 factorial, 4 factorial, 8 factorial, is it? So 12,
Yes.
11, 10, 8 factorial over 4 by 3 by 2 by 8 factorial. So that this piece and this piece goes. Then 4 and 3 takes away 12. 2 reduces 10 to 5. So you have now 55 by 9. So you get 45 there. Carry 4, 45. So we'll have 49. So meaning that this term is going to be 495 x power 4.
All right, sir. Thank you so much.
Okay.